Hello and welcome to EP2CM4 lecture number 3. This is going to be our second one on heat flow, advanced heat transfer, and computational vector calculus. So today we're going to be exploring three different topics on extending the work that we did last week on heat flow and dealing with the heat equation. The first one is going to be how to make really complicated well, at least more complicated geometries using the finite element method software we're using, FlexPDE. So specifically, we're going to look at circles to make cylinder type things and 3D geometries in general using extrusions. The next thing we're going to look at is integrals and how to integrate over a surface or perhaps a line boundary, how to integrate over a volume, or maybe an area, and then how to integrate with respect to time as well. And finally, we're going to look at different, more complicated load boundary conditions that let us deal with convection and radiation heat transfer at a surface rather than just a fixed temperature or an insulating surface like we were able to deal with last time. Okay, first up, we're going to look at how to make some circles in FlexPDE. This is a problem that we couldn't have solved last week with just rectangles. We're going to build on the region stuff that we did before to add in circular geometries and then finally 3D extrusions, how to make actual 3D shapes with this. Okay, so first we've got a heated rod that's at an initial temperature of 100 degrees C, and it's inside this steel casing that's initially at 24 degrees C. So the radius of the steel is 4 centimeters and the radius of the heated rod is 2.5 centimeters. And we've got some material parameters down here. We're asked to make a plot of the new temperature profile and heat flux density of the rod and the steel's central cross section. So this, maybe it would look like this. This is a cross section of it. Actually, this is perhaps long coming out of the page. After 30 seconds, if the rod and steel casing are very long, so we're just going to assume 2D approximation is valid, and if the rod and steel casing are only 20 centimeters long, and each of the two ends is held at 0. So then we're going to look at a real 3D modeling and just take a slice partway through this. In the interest of doing a bit of a review, we've got a brand new FlexPDE file here that we can build up into this problem. So we're going to call this maybe advanced heat transfer and computational vector calculus examples. We're going to use 2 dimensions still for the first one. We've got only one variable we're going to solve for, and this is the temperature. Because we're going to do time-dependent stuff, we need to give it a threshold of how much this is going to change before we need to look at it again. Let's say 1e minus 5, and then we will set up some definitions. So we'll set up some material parameters. Maybe we'll make the steel the default. K is equal to 59. Just move this a little bit so we can see the rest of those parameters. CP is equal to 502, and rho is equal to 8050. And then we'll specify different parameters in the rod region. Now initially, the steel is at a different initial temperature than the rod, so we'll have to make that a parameter as well. T initial is equal to 24, again using the steel as a default. Temperature is equal to T initial is what we'll set as the default value there. Now before we build in the actual differential equation, let's just put in temp and then make sure that we're drawing the boundary correctly. So we'll leave it as the square for now. We won't put any time dependent stuff, and we'll put a contour of temperature just so that we can test things as quickly as possible. So sure enough, everything is 24 degrees when we're just solving the Laplace equation on this, and we've got the square that we started with. Let's build this up and change the differential equation to the actual heat equation. So for that, we're going to have rho Cp times dt of temperature is equal to Q dot vol, volumetric heat generation, which is 0. And then we're going to be also, so next part of the heat equation, we need Q dot, the heat flux density is equal to negative K times gradient of temperature. So we're going to be subtracting off the divergence of Q dot. Just as a check that this works out from a theoretical and conceptual perspective, this side is the per unit volume rate of energy change. And this is telling us it's equal to the per unit volume rate of energy generation minus the divergence of the heat flux. So this divergence of heat flux means that it's kind of heat moving away from that spot. So that's why we subtract that off. Okay, so in other words, the rate of change of the energy per unit volume is the rate of energy generation minus the rate that energy is leaving from this little bit of volume. And that's the heat equation with its physical meaning. Okay, so now that we've got that in there, we have to add in the time that we're going to simulate for. We don't need any monitors, and we have to say a time that we want to plot it for. So for t equals n time, say. Okay, so this is 1 second later. Again, with only one piece, nothing happening. There's no change in the temperature from 24 degrees. That all makes sense. Next, the actual region that we want to draw. So we don't have to name this region 1. We can call it region steel. You can give it a name there so it's more descriptive, easier to read later. And to draw the cylinder of radius 4 centimeters, what we'll do is start at the right-hand side and then do an arc of 360 degrees to bring us back to close, with the center of the arc being the center of that circle. So let's make it, let's make this the origin. Then what we'll need to do is start at 4 centimeters, 0.04 and 0 and y. So that's this coordinate. If this is the origin, then that would be the point. Then this point over here is 0.04 and 0. And then we will say arc center equals 0, 0, angle equals 360. And this, if I haven't messed up the syntax, should draw a circular arc for us. Okay, there we go. Let's check it. It's 4 centimeters radius. We've got our circle. Still nothing's changing here. It's just 24 degrees everywhere. But we've drawn the steel boundary. The exterior of this is by default an insulating boundary, which is what we want. The outside of the steel is insulating in this problem. It told us that in the question. But just as an initial check, let's make the outside a different temperature. So we'll say value of the temperature is equal to 0. And what we'd expect is that we're going to have some cooling that takes place. Over 1 second, it's, steel, decent conductivity, but it's also got quite the heat capacity. 4 centimeter radius steel rod is reasonably large. It's not going to change temperature that quickly. So probably the outside will be 0 just right at the boundary, but then the interior will still be at 24 1 second later. Let's check. Okay, yeah. So right at the edge, we're at 0. This big circle all through the middle, still at 24 degrees. Let's make the contour filled in by typing painted and get a little bit prettier of a picture here of what the temperature looks like throughout this solid steel rod 1 second after having the exterior fixed to 0 degrees. All right, the next thing we're going to need is to draw the rod inside of this. So we'll make that a different region. Region rod. And for this one, we're going to set non-default material parameters because we made steel the default. We need to change them for this region, but we didn't need to do that for the steel. Maybe we'll add in some tabs to make this a little bit easier to read. Okay, so for the rod, we'll set K is equal to 0.03, CP is equal to 84, and rho is equal to 1600, the top row of this table here. And we also have a different initial temperature, which we're calling T initial, and that's 100. Then next thing we're going to do, before we forget, is get rid of this value boundary condition at the edge of the steel. So it's just a fixed insulating outer surface. Then draw the rod inside. And we're going to do this with a very similar command to what we did for the steel, except that we're going to use the rod radius of 0.025 meters, 2.5 centimeters, instead of the steel radius. Okay, so let's check. yeah, we've got this interior thing here, the rod, and it looks like it is around 100 degrees, a little bit higher with some error in there happening. It seems like it goes up to 112. That's not physical. It's not going to be heating up to that. That's just an error in the ability to calculate exactly what the temperature will be at this short time 1 second later, whereas the steel has actually cooled down in the boundary. It's gone down to 23.7 degrees rather than the 24 that it started with. That's just numeric error. The steel outside is not actually going to cool down when you have it in contact with this rod that's at 100 degrees. Okay, so the actual time that we wanted to simulate for is not 1 second, but is 30 seconds. So let's change this time here to 30, and then we should get a better picture of what's going on 30 seconds later. Okay, so it looks like the center of the rod is still at 100 degrees, so still fixed at 100 degrees or higher, and we've got now it going up only to 101, so not as much of an error. The minimum 25.8. This steel has been heating up, so it's heating up kind of uniformly because it's a much better conductor than this rod material is. So the steel seems like it's mostly staying at one temperature while the rod is heating up in the interior. One way to quickly identify if there's a problem like this, where the temperature is going above the starting temperature, is by setting a fixed range here. So on the contour plot, fixed range 24 to 100 from the starting lowest temperature to the starting highest temperature, and this will make anything that's above that show up as this blocked out area there. So this seems like somewhere where we probably needed more mesh density or more precision in calculating to get around the error that showed up in the plotting. You can also mess around with fixed range and try to make it less likely to show up that much in these slightly hot spots there by changing the range up until it all looks more or less the same. If you're lucky, then, and the temperature isn't too different in those spots compared to the ones around it, then you might be able to find a spot where this looks just all smooth in the center. If we set the range back to the starting range, then we can explore a little bit about how the parameters affect the solution here. So another thing that I've done is I've changed the number of grid elements to 15. So if you don't specify anything here, then Flex is going to try and do its own meshing idea. You can see this bouncing around and adding where it thinks it needs more elements, but evidently we're getting more error right in the middle. So this is definitely non-physical. So it might make sense to just override that and say just use this minimum grid density, and that seems to give a smoother solution through this interior region. Okay, so next thing we can do is again mess with some of the parameters. The rod is all at this very kind of slow temperature flow across this boundary, which we can explore by changing around the conductivity. If we make the conductivity of the rod 10 times higher, then what we expect is that the temperature is going to have changed in the middle more quickly after this amount of time. Probably the steel is going to be higher temperature after 30 seconds because a lot more heat has been able to transfer out of the interior part of the rod, not just the exterior part of it. So let's give it a shot. Yeah, it looks like the minimum has gone up from the, what was it before? 0.03. The minimum temperature at the edge was at 26.2. Actually didn't go up that much in the steel, only to 26.8. That's the extreme min temperature. Whereas the temperature in the rod seems to have reduced quite a lot as more heat has been able to transfer out from the interior part of this. We'll look soon at a way to figure out how much the temperature of the steel has actually changed when we get into integrals. Not so much the minimum temperature at any one spot in the steel that we're interested in here, but the average temperature of it over all of the region that the steel exists in. To get another feel for how heat is flowing, we want to make that vector plot of the heat flux density. and have a look at how this looks. So with K reasonably sized, we've got a lot of heat transfer right around this ring area right now, flowing out of the rod into the steel, and then towards the edge of the steel or the center of the rod, there's really not a lot of action there, not a lot of heat flux. If we move this back to the lower amount, then things get even more concentrated around that perimeter area. Nothing's going on in the center. There's no temperature gradient there to drive things. This is what it looks like when we've just got zero vectors. Zero vectors have undefined direction. So there's no heat flow in any direction in particular going on in the center, but right around this edge, we've got a very well-defined heat flow going out of the rod into the steel. So a little bit of notes here at the end. The regions over right, any regions that they cover that were defined earlier. So because the rod is smaller than the steel, it's we need to have this after the steel definition. If we put the steel after, then this is just going to overwrite what's going on in the rod. So now we've just got the steel, and notice that we have the steel temperature profile. Well, this is getting cut off as it's going just slightly below 24 at the top from its initial starting one of 24. This is just zero heat flux, as you can tell by the E-7 there. We've got just the steel temperature everywhere, and notice that when you have a default parameter like this, so these default parameters, even though you define parameters differently in this region, it doesn't overwrite the default from now on, kind of like how boundary conditions work. When you apply them on one part, they continue until you change them differently. Once you start a new region, then it resets everything to the default. So both the boundary conditions and the material parameters get reset to whatever their defaults were. Whereas if we put this back and put the steel before the rod, then because the rod redefines stuff that's going on inside the steel, totally fine. It's just going to replace what was defined in that part of the region. Okay, so next up, we want to make this a 3D geometry and see how things compare if we don't have this infinitely long rod and steel casing, but it has a finite length. The way to do this is with the is by extruding this shape. So we've got this shape drawn in 2 dimensions here. So we've got it in X and Y, and we're going to give it some depth in Z using the extrusion syntax. So that is in the example here that's continuing along, you have a reminder of the syntax. So before the boundary section, you put this keyword extrusion, and then specify names for surfaces of where it's going to start. The specifying the names just makes it easier for you to apply boundary conditions on those surfaces if you need to later. If you just want them to be, the default boundary condition, then you don't need to name them like this. You can just use a bit of a shorter syntax. But to keep it as consistent as possible and keep it as flexible as possible, just before this boundary section, extrusion, and we'll say surface Z equals 0, surface Z equals 0, 0.2. So right away, this isn't going to work because we haven't set it to 3D. So let's just show what that does. Illegal in 2D geometry. That error tells you need to set it to Cartesian 3. And now we're going to need to change some other stuff. So the differential equation still works all the same because the divergence and the gradient will just default to their 3D versions. The drawing of the regions in 2D will work just fine. The problem is these contour plots and vector plots need to know where we're taking them. So we are going to have to specify what exact part we want to take this plot on. So we can say contour on Z equals 0.1, I think, is the syntax, and then same thing here on Z equals 0.1. That would be in the middle. Okay, so it draws out the shape, but the problem is that we're specifying an n grid of 15, which is too dense for this. So let's try not specifying anything and just taking whatever FlexPDE gives us for the default. It takes a little bit longer to simulate. And when we're done here, we've got a similar looking temperature profile generally in the center. The region that's cut off is different because as you can see, we have a lot less grid elements across the cross section of this. So it's definitely a coarser answer to compared to what we had earlier for this top profile there. The heat flux density also a fair bit coarser than it was earlier. Okay, so now this is actually simulating. This should be exactly the same as the previous one because we made it insulating on the top and the bottom surface. We didn't specify that that's at 0 degrees yet. To get a comparison, let's keep 1 on this z equals 0.1. That's right in the middle. And we'll make a copy of these plots right near the end, maybe 0.01. This is going to be a slice right at the bottom surface. And this should be identical to this one once we're done here. Or I guess down here, yeah, these two will be identical to these two. Besides the different grid elements on the edge versus in the middle, the values of the temperatures are basically the same from one plot to the next. The location of the heat flux is basically the same. The size of it is more or less the same size. We got this green color around the ring here, and that's like a 300. Down here, it's not quite green. This is scaled differently, but we got more like a teal with these green spikes around the edges. Unfortunate that we don't have more mesh density to make this a little bit better, but this gives you the idea. Okay, so next what we can do is specify the boundaries on these surfaces, the boundary conditions. And to do that, we're going to first name them surface bot, say, and top. Then down here, before you get into the region specification, you can say surface bot and then specify a boundary condition. Value temperature is 0, say, and then same thing for the top surface. Okay, now what we predict is that by making this close to this fixed 0 temperature, everything is going to be dropping quite a lot. If we leave the bottom as 24, then this is probably just going to be all off the scale because we're only one. Let's see, where did we draw this? We drew it 1 centimeter. Yeah, 1 centimeter away from this 0 degree surface. So maybe the steel will probably be completely cooled off, but the rod has a lower conductivity. So maybe the center of it will still be visible on this color bar. Let's check. Yeah, okay. So the steel has dropped below 24 degrees, not necessarily at 0. It says that the minimum temperature anywhere is 7.62, whereas the rod has cooled down a fair bit. Now, interestingly, the rod has cooled down more at the edges than it has in the center. The reason for that is because these edges are closer to the steel, and the steel can act like a superhighway for getting the temperature out of this thing. Rather than looking at this cross-section across the center, oh, by the way, the center point in the middle of the rod seems like it hasn't changed at all, really, by the existence of these boundaries. So it's too far away for their influence to have permeated in after only 30 seconds. We can get a better picture by looking at a different cross section, rather than let's keep one of these cross sections and let's change the other one, the top one, which wasn't doing anything that interesting, into, well, first of all, let's get rid of this fixed range stuff and just look at what it looks like on the default full color scale. Right, so now we can see a little bit more clearly. We're going down to 7 in most of the steel there, and we can see the temperature across this one still staying basically the same. Yeah. So next, different cross section. Rather than on Z equals 0.1, let's take this on Y equals 0, or equivalently X equals 0. We've got cylindrical symmetry here, so this is going to take Y equals 0 would be a slice through the center, looking along the length of the rod, now in the top picture there. So what this will show us is how the heat of the rod is changing compared to like along the length. So this also has the information across the center here, right? Giving us the same kind of picture as the circle was giving us before, showing us that we've cooled down. We're basically at this starting temperature around 24 in the steel here. Maybe it's actually heated up a little bit. It looks more like 25 because of the influence of the rod like before, but the edges at 0 are cooling down the edges of the steel quite quickly, and that's kind of helping to pull heat out. So you'd expect that the prevailing heat flux density is outwards radially, like before, mostly around this junction between the steel and the rod here. But down here, there's going to be a lot of heat flux density just going towards the ends as we send heat towards those 0 degree surfaces. And that's what's going on here. So yes, moving out of the rod into the steel and flowing down and out through the edges of the steel into that 0 degree surface. Now you may have noticed that the notes actually uses 0.3 for the conductivity rather than the 0.03 that was given in the table. That's because some more interesting stuff happens at that point. If we switch this to 0.3, then a lot more heat flux will be happening in the rod after 30 seconds. It's closer to the steel. We can resolve things more easily, and we'll see a lot more heat flowing out of the center of the rod and filling out these pictures a little bit better. Let's give this a shot. So increased the thermal conductivity of that rod material in the center. What does it look like in 3D? And yes, we've got this central sort of hot portion still in the middle of the rod, but there's a lot more heat flux taking place outside of it. We now have a max temperature, not 100, but 90. So we just started to change the temperature right in the middle of the rod after 30 seconds, and a lot more clear what the heat flow is. So flowing out from the middle of this rod towards the steel, finding the quickest path that it can, taking these like high-speed highways for heat flow in this higher conductivity material out in the edges. The next thing we want to do is have a look at some averages, so we can get some of the information that we wanted to know earlier by looking at averages over regions, and we can do that using the syntax for integrals in FlexPDE. So there's some examples here that will go through a different rectangular geometry, but I'm actually going to modify these for this circular geometry that we're dealing with in this problem, just to give an idea of how this works for the volume integrals at least. Okay, so there's a few different integrals you can take. If you just use the syntax integral and then give it a thing that you want to integrate and then a region name, then you will be able to get that quantity over that region. So let's explore this a little bit. If we say report, so summary first, summary, and then report. Imagine we wanted to figure out the average temperature of the rod after 30 seconds and compare that to the average temperature of the steel. Then we could report integral of 1 over the steel and report integral of temp over the steel. So this quantity is going to be the volume because we're integrating 1 over the steel. This quantity is going to be the temperature integrated over the whole thing. So if we take this quantity and divide it by this quantity, that will be the average temperature. Volume of the steel. Integral of temperature over the whole steel. Well, that is proportional to the total energy, but we would need to multiply it by rho and Cp for it to actually be the thermal energy inside the steel. even then we'd have to put the temperature in absolute terms. So let's just leave this as this intermediate quantity here, and then we'll have this as the average temp steel. Okay, let's give it a shot. See if the syntax of that works out before typing too many more of those. All right, so it says the volume of the steel is 6.13 E-4 cubic meters. Because we're all in centimeters and it's this annular region, we don't expect it to be that high. The integral of temperature over that thing, 0.0138. Again, this is proportional to the volume. But if we divide the volume out, then we have the average temperature, 22.56. That seems reasonable because we are mostly ending up at still kind of close to what the temperature was at the start, 24. In the interior region, it's actually heated up a little bit, whereas towards the ends, it's cooled down, and we end up with just a little bit lower than the temperature of the steel to start with. We could repeat the same thing for the rod by using the same syntax, but using rod as the region here instead. Average temperature, rod. Yeah, rod. There we go. Okay, so the average temperature of the rod has cooled down a fair bit more, 47.9 degrees, rather than just this 22.56. Let's switch this into the two-dimensional version to see how things compared there. So we'll save a new file, 2CM vidwork, maybe 2D version, and then we'll go back to 2D from this 3D version. So switching it to Cartesian 2, we'll get rid of the extrusion. We'll get rid of the boundary temperature specification. We will change these to not specify a surface anymore. The first contour plot no longer is going to work. The second contour plot of this cross section now doesn't need a location anymore, and I believe, if we haven't forgotten anything, then we've successfully switched back to 2D. All right, so in 2 dimensions, we have that the average temperature of the steel is raised up a little bit. Now there's nowhere that it can flow out the edges, and the average temperature of the rod is higher than it was before, but not by quite that much. So 54 compared to 49. The average temperature of the steel, in an absolute sense, has changed by even less. Now let's see. We were talking about the effect of K. So if we change this to 0.03, then what we expect is that the rod will be at a higher temperature. The steel will be at a lower temperature. It will not have heated up quite as much. So let's check this. Yeah. So the rod is now at 83. The steel has not heated up quite as much as it did before, only at 25.9, with less heat able to flow out of the rod in the center. The reason that it makes so much less of a difference to the steel is because the steel just has a lot more heat capacity, right? So the amount of heat that steel can hold is dependent on the volume of the steel and the heat capacity of the steel, and so the specific heat capacity multiplied by the density. If you take the density and multiply by specific heat capacity, so specific heat capacity is in joules per kilogram Kelvin, density kilograms per cubic meter. So together, this is going to be joules per cubic meter Kelvin. If you multiply that by the temperature, then we have something that's proportional to the internal energy change compared to 0 degrees. So if we were to take maybe this minus T initial, then this quantity that we're computing is the increase in energy. Increase in steel thermal energy. We can try to do a similar quantity for the rod. Let's change this to temperature times, so the temperature difference times Cp times rho as increase rod energy. Now we expect this one to be negative, and since the outside is insulating in this problem, all of the energy that has gone into the steel must have come from the rod, so it should be equal and opposite to this other quantity here. Let's see. Extra bracket. Okay. So that's actually off by quite a lot, which means that there is likely some error. Let me see if I can track it down. Okay, we're back. Yeah, it actually turns out that that is legitimate error in how the calculation is being done. It's not actually to do with the way that we're calculating the integrals, and this is all the more reason to just check your numeric results and listen to the lesson that even though the computer has, whatever 24 decimals of precision, doesn't mean that it's always right. We've only got so much grid density that we can use along this edge, and that can lead to problems over the length of a long time-dependent simulation in terms of what temperature we end up with on each part. To see this a little bit more clearly, I've got some experiment here to demonstrate. What you can do is change the final time to a long enough time that everything has just settled down, and change the material parameters around so that we can explore what's going to what the final temperature should be. So here I've changed the parameters of the rod. I've left the steel the same, and we're still working with these circles, and we can see what the final temperature should be. So now we're doing, area integral is the same thing as integral, the integrating energy density over that region. And energy density I've defined as the temperature minus the initial temperature times the specific heat capacity times the density. And I've gone and explored that, yes, it does indeed include all of these different parameters here. Just to do a complete check, I'm even calculating this with Maple as well. So that's this calculation here. Using the steel parameters up in the top and the area of the steel, we can take the final temperature that we get here after we wait a long time, 27.19, and then see what the energy increase of the steel is by integrating, really multiplying the final temperature that we get minus its initial temperature times its density and specific heat capacity and volume. If we're at a unit depth, then the area is proportional to the volume, and we find that the increase in energy of the steel is 39.486. So that's pretty close to the increase in energy of the steel that we calculated here in FlexPDE after it's all done, and we've ended up with this temperature. And similarly, the decrease in energy of the rod, if the rod has the same final temperature, 27.19, is 19.214, and we've got 19.212 in FlexPDE, so very similar calculations for the integrals. Integrals are working perfectly fine. The issue is that this is not the correct final temperature. So it's the differential equation solving which actually is giving us issue in this. The final temperature, in order to conserve energy between the rod and the steel, should actually be somewhat smaller. So if we try 26.19, then we get closer to the same energy change. If we try 25.19, then we've gone too far. So the actual final temperature may be something like 25.59. Yeah, that's pretty close. So we're off by about maybe 1.5, is that right? 1.5 degrees from where we should be in this final temperature. So the error that we've ended up with over this calculation, going from 24 and 100 and evening out, has been pretty significant here. even in this situation where we've changed the parameters of the rod to be a little bit more realistic in terms of the heat flow. If we change it to a 0.03 so that things are going to take a fair bit longer, maybe we increase the time, then we can see how much this is going to affect the final answer as well. This should have no bearing on what the actual final temperature is. It should just take longer to get there, which means we have more opportunity for numeric error to add in. So we'll see what the temperature is now. So 27.19 didn't actually change that much. So more sensitive, not to the time that it takes to get there, it seems, but to the just raw difference in material parameters. If you make these parameters closer together between the rod and the steel, we can do that by getting rid of those. So that now the rod uses the default parameters for the steel. Then we can modify this to say just be the steel parameters, 8050 and 502, and see what the final temperature is. It looks like the final temperature 53.57. And that gives us a much more realistic, much more reasonable change in energy, where the amount that the steel has increased is the amount that the rod has decreased. So seems like the very different amount of energy per unit volume stored in the rod is what's tripping up FlexPDE in this example. Another check we can do is try to find the amount of heat flux leaving that boundary between the rod and the steel. So we can do this by naming a path. So saying start, and then right after start here, in this place where we draw the arc of the rod, we can put in a name. So we can call this rod boundary, and see that nothing changes. Everything's good. We're still able to do the simulation. And what this is going to let us do is do a line integral around the perimeter, which in 2 dimensions is the same as a surface integral in 3 dimensions, because this is kind of like an edge of unit depth. Out from this spot. Let's change it back to 30 seconds so we don't take forever with this simulation. We can just look at this point. With the equivalent material parameters, we have much nicer change in energy, but let's check out how the heat flux works. So we will do report line integral of normal of Q dot. And where? Well, over the rod boundary. And this should be giving us a net flux out of that, out of the rod. So at this point, we've got 2562 as the total heat flux coming out of the rod. So that's this amount here, integrated around that. Again, you can do not just line integral, there's some other names for this. So you can call this a B integral for boundary integral, or a surf integral, I believe, for surface integral around the outside of this. Yeah, so 3 different names for exactly the same thing, up to you what you want to call it. The normal of Q dot will be taking just the perpendicular component to this boundary and integrating that around that edge. We can check that this has given us the right answer by taking this total heat flux out, right? This integral of normal of Q dot through the edge of the rod is the heat flux out of the rod, and integrating that thing with respect to time. So we can maybe make a name for this. Let's copy that and put it up here. Net heat flux out of rod is equal to this thing. And then we'll try to find the total heat flux out by integrating that with respect to time. So to find the total amount of heat that's traveled out, we can use time integral on this. So we'll say total heat out of rod is equal to time integral. of net heat flux out of rod. So we'll try to report that. Let's give that a shot. Okay, so total heat that has gone out of the rod is 172,475, and notice that this is equal to roughly the increase in the steel energy and roughly the decrease in the rod energy. Again, with a little bit of a numeric error in this, not quite the same as what we had earlier up there. We can see how sensitive these various parameters are to the changes in the parameters of the rod. So if we put everything back to the actual default and then try and calculate this again, then we can get an idea, we can get an impression of which things are off by the most. So in this setup, we see that the rod has only lost 4 kilojoules, but the steel has somehow increased in about 25 kilojoules. And even though the rod has, so the rod has lost 4 kilojoules, we got this change in energy of the rod by about a similar amount. So this total heat out of the rod seems like it's agreeing pretty well. The reduction in temperature of the rod, therefore, is actually going to be more than this on average, and the increase in the temperature of the steel is going to be not quite as much as this. With the vastly different material parameters, we are making it difficult with the amount of grid elements that we can get in the student version. All right, the last topic for today is convection and radiation at boundaries. This is a little bit more on the theoretical side. So rather than having just a fixed temperature or zero heat flux, another common boundary condition is that you have convection. So some fluid is interacting with the surface and carrying away heat from a combination of conduction right at the boundary and then fluid flow that moves it away more effectively. Convection is typically modeled by looking at the total, saying that the total rate of heat flow away, or maybe total rate of heat flux away from the surface, is this H, the convection coefficient, multiplied by the surface area, times the difference between the surface temperature and the free stream temperature of the fluid, the temperature of the fluid, the air or the water, far away from that surface. In a per unit volume sense, you would just have this same thing divided by the surface area. And that would be your heat flux density from convection, H times Ts minus T infinity. Radiation, we can also say that the rate of heat transfer is proportional to the surface area, except with different parameters in front. So it goes like the emissivity of the surface, which is equal to the absorptivity of the surface, the Stefan-Boltzmann constant, and the temperature to the power of 4. Now, because of this, it's not just a difference in temperature. This one needs to be absolute temperature. So you need this one in Kelvin. The net radiative heat transfer. So if you've got an object interacting with its surroundings, then just like you could have heat going out from radiation, you can have heat coming back in. If the surroundings are all at the same temperature and are much larger than the object, then we can write that the net emissivity in that specific case is not net emissivity, the net radiative heat transfer, I should say, in that specific case is the same thing, but with a difference between the 4th power of the temperature of the surface and the 4th power of the temperature of the surroundings. So a lot of the time what you can do is combine these mechanisms into a total rate of heat transfer, the convection plus the radiative heat transfer at that surface. And if you write the sum of them like this, you can use a little bit of algebra and define this combined heat transfer coefficient, where the combined heat transfer coefficient is the convection one, plus this term that's pretty temperature dependent that collects all of the radiative heat transfer stuff all together. The heat transfer coefficient, even if it is just from convection, ends up being quite dependent on a lot of parameters that are going on, like the fluid velocity, the roughness of the surface, the shape of the surface, how it's flowing past that, the temperature of the fluid and of the surface can affect things. So this is kind of a complicated parameter. And in this course, we're just going to give it to you, but there's whole courses or even fields of study and careers on figuring out what convection or combined heat transfer coefficients are for different situations. So for us, we're going to make it quite a lot simpler and say that the net heat flux density from a surface is this combined heat transfer coefficient times the difference between the surface temperature and the surrounding temperatures. Again, there's a lot of detail in this, but once you've figured it out, then you can model convection and radiation together like this. To incorporate this into FlexPDE, as long as we have this standard form heat equation, so like the regular one here, or maybe even the steady state, no volume generation stuff, any one of these kind of heat equations where we haven't gone and factored out the K from this interior part and moved it over to the other side, then then what you would do is say load of temperature is H times the temperature minus the surrounding temperature that you want. And that's how you can incorporate convection. Let's explore this a little bit. So if we take this example, rather than having the exterior boundary of the steel just be insulating, let's put in a convection boundary here. So we'll say load of temperature is equal to, now we'd put in the H value. So who knows what the H could be? Maybe it's 7 times temp minus the surrounding temperature. What should the surrounding temperature be? Maybe the surroundings are at 10 degrees C. So it's kind of cold out. We're in some sort of cold room there. We don't have, we're not scaling the contour plots, so this should still work. And now let's check this out. So what we expect is that the steel is kind of cooling off on the perimeter a little bit from this convection. Not very much though, because this is actually a very small convection coefficient. We can increase this quite a lot up to higher values and see what we get. The higher this goes, the closer we'd expect after 30 seconds we get towards 10 degrees on the surface. So another factor of 100 stronger convection should really help with this. Yeah, now we've definitely stuck to 10 degrees. You see a massive amount of heat flux out the edge. A lot of detail happening in this convection coefficient right here. If we go somewhere in between there, 7,000, then we still have basically 10 degrees on the exterior surface. But with 700, now it's at about 20 degrees. So it's cooled down a little bit, but not a lot at this exterior surface. One really tricky thing to watch out for is the way that a load boundary condition works on a variable is that it sets what the constant will be after you do one integral of this like second order differential equation here. So it's setting what the derivative is, but it's in terms of not the original variable, but the way that the differential equation is actually written. So let me explain that a little bit. This load is roughly the directional derivative going out of the boundary. So as we leave the boundary, we have this load of temperature, which because we've written the differential equation in terms of Q dot tells us exactly what the Q dot will be, what the heat flux will be. But if we take this differential equation and we write it differently, let's first write it exactly the same, negative K times grad temp, just to show that this does nothing differently. We're going to have about 20 degrees on the outside. Yep, there we go. 20.1 is the minimum temperature there. If we take this exact same differential equation, keeping the bracket in there at the end, and rather than this one, we take the K out of this. We put -1, and then we factor the K out front, and then we in fact move it over to the other side of the differential equation. So we do this divided by K, and even though Q dot vol is 0, we divide by K there as well. Let's see. Now we have a vastly different situation. So this has increased the effective convection by a huge amount there. So now we've got something that is scaled up so much and is cooled off the steel by a fair bit. So this is because the differential equation now is assuming that this is what we're going to get when we substitute stuff in and after we've done the integral. So this is now saying rather than k times grad temp is equal to 700 times temp minus 10, it's saying that 1 times grad temp is equal to 700 times temp minus 10. So to be safe, don't mess with the differential equation and keep it in terms of this regular form so that it's written with heat flux over here, and then your load boundary conditions will be able to specify heat flux directly. So if you want this to be H times the temperature minus the surrounding temperature, telling you the rate of heat flux from the surface, then keep the heat equation in the standard form, and everything will work out. Okay, thanks for watching. Have a great day.